Okay, so let me start with a few announcements. The first announcement is that I have not had time to look at the midterm, so I haven't looked at any of your midterms exams, so I cannot comment on how well you did. However, I did notice that for a number of you, finding the right control volume sometimes was difficult, and how to carry through a control volume analysis was still a challenge. So I think you need more practice on that because it is fundamental. You've seen some example of that in your bachelor's, but it's still a difficult method. And so the second announcement is that as a consequence, I've decided that on Friday we will dedicate the 2 hours on how to carry through a control volume analysis. So there will be an example on which you can work, and then I will let you try to first find the right control volume, and then carry through the control volume analysis. So computing the stresses and the fluxes on the control surface. So that will be on Friday. I think it's a good thing. So I'm not doing it today because I couldn't give you a notice about this. So for Friday, it will be good if you prepared for it by reviewing problems and coming with questions. And so now coming to what we will do today. So today we're going to continue where we left it off, where we left everything 2 weeks ago. So we will finish our part on vortex dynamics in the first hour, and then in the second hour we will start our discussion of irrotational flows. So as you've noticed, I cannot be here at this particular hour, but Koen should be here. And so what I will do is try to keep the lecture part, so the recorded part of the lecture, shorter to 35 minutes, 40 minutes, such that you have the chance then to ask questions to Koen. So in principle, the video should be roughly anywhere between roughly 35 minutes, which will give you a few minutes to ask questions afterwards. But the video will be uninterrupted. Okay, and so before we go into the vortex dynamics, I think it's good at the beginning of the second quarter to remind ourselves of where we are in the flow of advanced fluid dynamics. So let me go back to our very first lecture, and let me go back to our roadmap. So this is the roadmap that we sketched together during the first lecture, and we've been busy with parts of it. So the first part, what we started with, was to discuss dimensional analysis. And this is something, of course, which will continue to show up in advanced fluid dynamics, which allows us to see what are the important physical phenomena and what are the important terms in the equations. So that's the first thing that we discussed. And then we started a long part on deriving the governing equations for fluid motion. Those are the Navier-Stokes equations. So we derived the mass conservation equation, which in the differential form is called the continuity equation, or the incompressibility condition when we assume compressible flows. And we applied Newton's second law to continuum and then to fluids, and derived the Cauchy momentum equation and later the momentum equation of the Navier-Stokes equation. So those are the most important equations, and in a way, once you've seen and once you understand the Navier-Stokes equation, once you understand mass conservation and the momentum equation, you can, the work is done. You can pretty much do and solve any problem in fluid dynamics, provided you know how to find a solution. So that's, in many cases, the difficult part. But so we were busy and we derived the governing equation, and we discussed a small particular flows, and those were inviscid flows which were steady. So we derived the Bernoulli equations, but you will see that we will come back to the Bernoulli equation starting next week. And what we did during the last lecture was to discuss another quantity which is of great relevance in fluid dynamics, which is vorticity. And so we'll finish that today. Now, after that, what we will do for the second quarter is first we will neglect the viscosity term in the Navier-Stokes equation, and in particular we will focus on flows which are irrotational. And we'll see that when a flow is irrotational, then it is inviscid. So we'll first discuss steady flows, flow around the cylinder, which is very relevant to aerodynamics and to how you model flow around airfoils. We'll also discuss unsteady flows. So what happens when the flow is time dependent, when objects accelerate, for instance, in a fluid, and that will introduce the concept of added mass. So this will keep us busy for 3 weeks, so until week 11 at least, 11 or 12. And then in starting week 12 or 13, we will start discussing what happens when we introduce effects of viscosity. So the first topic we'll discuss in viscous flows are boundary layers, because boundary layers make the connection really between between an inviscid flow far away from a boundary, and how do we still take into account the effects of viscosity and apply a no-slip boundary condition at a wall. Those gives rise to boundary layers. And then we'll discuss more general viscous flow, laminar flows, and in particular flows in a particular geometry of thin films, which is called lubrication theory. So this will keep us busy for another 2 weeks. So by then we'll be at week 14 or 15. And then in week 16 and 17, we will discuss instabilities, which are of great relevance in fluid dynamics. So we'll discuss gravity waves, and if we have time, we'll discuss the Kelvin-Helmholtz instability. So this is the plan for the 7 coming weeks. But now what we are going to do is go back to our discussion on vorticity. And now, of course, since it's been a while that we've discussed that, I have to just make a quick summary of what we've seen. So we've been discussing vortex dynamics. The first thing that we discuss are just definitions. So the vorticity is a vector field. So just like the velocity field, it is defined at every single location at every single time. It's a vector field which is equal to the curl of the velocity field. And we discussed that the curl, you can also see the short concept clips that you have in the lectures. The curl represents the rotating part of a vector field in a way. The part of the vector field which rotates. So this is what vorticity is. We discussed another quantity which is related to vorticity, which also has to do with how a flow field rotates, and that is the circulation. Now the circulation is a scalar, so oftentimes it's called gamma, and it's a scalar which is associated with a particular contour. A contour is just a closed curve. So if this curve here is closed, this is now my contour, and the circulation is defined as the line integral over a closed contour of the flow velocity field. So it is the integral of u, which is the velocity field, dot dl. And dl is a differential element of displacement along c. So the direction is tangent to the contour, and the length is just a differential length. So a small delta of length. Now the two are related through the Stokes theorem, and this is what allows us to interpret a little bit what the vorticity is. So the Stokes theorem indicates that the circulation, or the line integral of u dot dl, is in fact equal to, and there is no physics in that, this is just a mathematical this is a mathematical expression, it's equal to the flux through an open surface attached to the contour. So you now have to imagine that this here is my contour, closed contour. Now there is flow. What that means is that you have, so here I'm representing streamlines. Let's assume the flow is steady and that these are streamlines. You have flow. Hold on, this is a bit confusing. So you have flow, but I'm not going to be talking about the flux of the velocity field. I'll be talking about the flux of the vorticity field. So here you have velocity u. You could compute the curl. That would give you another vector field. Now you have to think about a surface which is attached to the contour. So this is a hat, and this is now my surface S. So this is an open surface. The surface S is open. And so the Stokes theorem, which again is just a mathematical expression, tells you that the line integral of u dot dl is equal to the flux of the curl of u, so the flux of the vorticity, coming out of my surface ds. So it is the double integral over the surface S of the curl of u dotted with the normal vector n. The normal vector n is of course just defined at the surface. So if here I have a small piece ds of surface, n is the unit vector pointing normal to the surface. And so if you want to think about what is the vorticity, well, you can think about shrinking this contour C to just a small contour around a single point, and then the vorticity will tell you, how big the circulation is on this very tiny contour at a given point. So the vorticity is really a measure of circulation, of local circulation, so of how much a velocity field rotates. Okay, so those are the definitions we introduced, and then we discussed three important flows. So those are very generic flows, which you have to know. And the first one was solid body rotation. So I plotted the vector fields on MATLAB. You can also just use the routines which we used at the very beginning of the class, just so that you see that what the vector, what the flow velocity vector, the flow velocity field looks like. So you need to be able to write. You have to be able to write the vector fields both in cylindrical or in polar here and in Cartesian coordinate. In polar coordinate, it's the easiest. So if you have to write the solid body rotation, you simply say that the radial component of the velocity, so the component of the velocity which is pointing away from the origin. So if this is here the origin. At this point here, my radial component is in this direction and the circumferential component is in this direction. So in the radial component I have 0, and in the circumferential component I have a vector which is linearly increasing with r. So you see that the magnitude of the velocity vectors are linearly increasing as I move away from the origin. This is how you would write it in polar coordinates, and that here is how you would write it in Cartesian coordinate. And you should convince yourself that those two vector fields here are equivalent. Now for solid body rotation, we did compute the vorticity. In 2D, you can think of the vorticity as just a scalar field. There is only a non-zero component of the vorticity vector in direction pointing out of the plane. So if this is x and this is y, then there is only a non-zero direction, a non-zero component to the vorticity vector in the z direction. So this is why you can just write it as a scalar. And the vorticity is constant and equal to 2 times omega, where omega is the rotation, the angular velocity. So this is a solid body rotation. The second flow that we discussed is the rotational vortex. Now the rotational vortex is a vortex, so it also looks like a flow which is turning around. And if you have to write it in polar coordinate, then again, there is no component of the velocity field in the radial direction. And now the component of the velocity in the circumferential direction decreases in 1 over r. So you see it here on that plot. If this is the origin, as I move away from the origin, the magnitude of the velocity decreases. So here you can't see, but if you zoomed in, you would see a very tiny vector in this direction. Again, in Cartesian coordinate, you can also write the velocity field. It takes this form, and if you are uncomfortable with that, well, do practice and make sure you're able to go from one back to the other. Now, when we computed the vorticity for that field, we found that the vorticity is equal to 0. So there is actually no vorticity anywhere here in the bulk of the fluid. That being said, you see that there is a singularity. So if you think here about x and y going to 0, or this is in Cartesian coordinate, or if you think about in polar coordinate r going to 0, so you're getting closer to the origin, you see that as r goes to 0, u theta is going to go to infinity. So u theta blows up, and in fact you cannot compute the vorticity at that particular point. It's not defined. So really the vorticity is equal to 0 everywhere except at the origin. So it's important, and what we discussed is that really an rotational vortex, you can think of it as a flow where there is vorticity nowhere except at the origin, where you have an infinite amount of vorticity. And now finally the Rankine vortex. So the Rankine vortex is a model vortex which does not have a singularity. And the way you define the Rankine vortex is, now I'm just writing it in polar coordinate, is to say, well, the Rankine vortex is an irrotational vortex, but it's only an irrotational vortex far away from the origin. So you define a radius r0, right? And in this case, particular picture here, r0 is equal to 1. So this is the velocity field for a Rankine body. 1 here is roughly here, right? So if you draw a circle of radius 1, you will see that anywhere outside of, if r is larger than r0, so in this region here, you do see that as you're moving away from the origin, the vector field decreases, the velocity decreases, and decreases in 1 over r, so you have an irrotational vortex. In particular, that means that if you computed the vorticity in this region, so in this region here, in all of that region, if you computed the vorticity, it would be equal to 0. So far away, the vorticity is equal to 0, but when you get closer to the origin, you don't model the flow as an irrotational vortex. Instead, you model the flow as a solid body rotation. So this is what you have here. So you model it as a solid body rotation, and therefore you see it here also on the velocity field. You see that as you move away from the origin, the velocity field here increases linearly with r, the distance to the origin. And so inside of the core of the vortex, so this region here you would call the core of the vortex, and the vorticity is not zero, it's constant, and it's equal to 2 times, again, the angular velocity, which you have to define as gamma divided by 2 pi r0 squared to make sure your component, your circumferential velocity is continuous. Okay, so, and finally we got to the vorticity equation. So we started from the momentum equation, from the Navier-Stokes equation. And we took the curl of this equation to find an equation for the vorticity. And the equation is the following. You have the material derivative of the vorticity, which is equal to the vorticity dot gradient of u plus mu, here mu is the kinematic viscosity, times the Laplacian of omega. Now, this middle term, so you have three terms. Let me call them 1, 2, and 3. This middle term here represents, it does represent a creation term. So if this term here is non-zero, this will create vorticity. And that corresponds to vortex tilting, so the rotation of a vortex, and vortex stretching, which is, those two things are important in turbulence. So if you take a class in turbulence, you will see discuss this term in more detail. Now, in advanced fluid dynamics, we will not really discuss this term all that much, and one of the reasons is that we mostly look at two-dimensional flows, and for a two-dimensional flow, this term is equal to 0. So this is equal to 0 for 2D planar flows, and so we won't discuss it in too much detail. This term represents the transport mode of vorticity, which is diffusion. It's a Laplacian of omega. So you recognize here the Laplacian, the diffusive term in the diffusion equation. So this really represents the diffusion of vorticity. And here the first term, this is the material derivative, it represents the advection of vorticity. So the time changes of vorticity if you follow a material element. So this is the advection of vorticity. Okay, so just to make sure you see how vorticity can be transported, we'll take two examples to discuss first what it means for vorticity to diffuse and what it means for vorticity to be advected. So the first thing we'll discuss is the diffusion of vorticity. You know what, let me just change those numbers here. Well, I was going to call this 1 here and this 2, because I'm first going to discuss the diffusion of vorticity. So number 1, let's discuss the diffusion of vorticity. The diffusion of vorticity. So we're going to start with an irrotational vortex. So let's assume we have an irrotational vortex here. Let me represent it as that. I have a point here. And at this point I have an irrotational vortex. And let me call the circulation gamma, the circulation around this irrotational vortex to be gamma. Okay, so let's say that we start with a flow. Consider that at time equals 0, the flow field is the flow field of an irrotational vortex. The flow corresponds to an irrotational vortex. Now, what happens to this flow? What happened to the vorticity as time passes? So let's write the diffusion equation. Let's write, the equation for the vorticity. So equation for the vorticity is the material derivative of omega dt is equal to mu times the Laplacian of omega, right? Let me just write here to make sure we are assuming the flow to be 2D planar. Right? The flow is 2D planar. Therefore, this term is equal to 0, so we don't have to worry about that. And given the geometry of our problem, knowing that the rotational vortex really has a sort of circumferential symmetry, we will write the equation in polar coordinates. So let me write the advection diffusion equation in polar coordinates. So that would be partial omega over partial t plus u grad omega. So this will be equal to plus the radial component of u partial omega partial r plus the circumferential component of u divided by r times d omega d theta. This is the material derivative of omega is equal to mu times 1 over r partial r times r d omega dr plus 1 over r squared second partial of omega with respect to theta. Okay, so given the initial rotational symmetry in the problem, we can safely assume that nothing is going to depend on theta. So the distribution of vorticity is not going to depend on the angle theta. So I can cross these terms here. And on top of that, at least at the beginning, but we'll see that if you have an irrotational vortex, the flow velocity doesn't really, the velocity field doesn't change, and ur is equal to 0. Okay, so ur is equal to 0. We have no radial velocity. So the equation reduces to just the heat equation. So partial omega partial t is equal to mu 1 over r partial over partial r times r partial omega over partial r. So this is the equation that the vorticity will satisfy. So here note that because there is no radial velocity, so there is no mass transport in the radial direction, then the only way vorticity is transported is because of the diffusion term. And so this equation you've seen before. This is really a diffusion equation or a heat equation. And so what will happen to the vorticity is exactly the same process as what would happen to heat or to temperature. Temperature, if there is no advection or heat, so heat, if there is in the absence of advection of flow, it simply diffuses. So we will not derive the solution to this equation, but we will just discuss we'll just discuss how it looks like. So we start at time equals 0 with an irrotational vortex, and as we've discussed, we can think of an irrotational vortex as a particular distribution of vorticity where there is no vorticity anywhere except an infinite amount of vorticity at the origin. So this is a 2D planar flow, but to simplify the graphs, I'm just going to represent one direction. So this is, let's say, the x direction, and I'm just going to graph the vorticity. So here I'm plotting the vorticity, and so at times equals 0, the vorticity really is equal to 0 everywhere except at the origin, where I'm going to put the point here, but really it's at infinity. We have an infinite amount of vorticity. This is a delta function. So we can think about the vorticity as really a delta function. And in total, once you integrate, you know that you're going to have gamma, so the circulation amount of vorticity. So this here is at time equals 0. Now later on, what is going to happen, just imagine what would happen if that was temperature and you just had 0 temperature everywhere, except at one point you have infinite amount of temperature. Well, you know that the heat will diffuse, but the total energy, so heat, will be conserved. So as this peak broadens, the maximum value is also going to decrease, and what you will start seeing is solutions that look like this. Actually, the solution to this equation is a Gaussian. So this is at a certain time t, and then later on it would look more like that. This is a Gaussian function, and even later on it would look more like this. This is how temperature would diffuse. This is also how vorticity will diffuse. So here the solution is a Gaussian. Gaussian is the solution. If you think about the area underneath that curve, this is the integral of the vorticity. This will be the circulation. So the area underneath that curve remains constant in time, but the peak decreases. The maximum value of the peak decreases, while the typical width of the peak of the Gaussian increases. This the width of this peak is defined by the standard deviation, and that standard deviation, if you've seen it before, for a diffusion problem, this length scale over which vorticity has diffused, this length scale L here, scales with, and this is very important, this length scale scales with the square root of mu, the kinematic viscosity, times the time. Right, so this, I should say, this is at time t, and here, as the peak decreases here, this is time increases. Let me just say here that time increases. So this is t equals t1. This here is, sorry, that one. Let me just start it again. Now write this in blue. This here is time equals t1. This here is time equals t2. And this here is time equals t3. Okay, and so as time advances, this length, the characteristic depth, width, sorry, of the Gaussian, so which represents the distance over which vorticity has diffused, scale with the square root of mu divided mu times t. Now this is a scaling which you could have gotten just from dimensional analysis. You could have just started from dimensional analysis saying that I have viscosity, so it's mu, and the only other parameters I have is L and T, and I'm trying to come up with a length scale. You would find that L has to scale with the square root of mu times T. Okay, so this represents the diffusive transport of vorticity. Now, note that if you have no viscosity, so when the viscosity is very, very low, then vorticity does not diffuse. Okay, so if you assume the flow to be inviscid or the fluid to be inviscid, then in that case, that means essentially you neglect that mode of transport. You neglect the fact that vorticity diffuses. So let me state that again. if you have an inviscid flow, if you assume the flow to be inviscid, that corresponds to saying this term here is negligible, and therefore you neglect the diffusion of viscosity. So an irrotational vortex, for instance, if you assume the flow to be inviscid, then will remain an irrotational vortex. The vorticity will remain concentrated just at one single point. If you assume the flow now to be viscous, then in that case the vorticity diffuses. So if we are going back now to the image of the Rankine vortex, right, you could model a vortex, a real vortex, as an irrotational vortex. If you start with an irrotational vortex and you take into account the diffusion, you could model it or represent it with a Rankine vortex, where the core of the vortex here, R naught, scales with the square root of mu times t. Right, so you would have a rotational core, so a core in which you do have vorticity, where the vorticity has diffused, and then you have the outside, which looks like an irrotational vortex because the vorticity hasn't yet diffused in that region. Okay, so this is the diffusion of vorticity. And now the other part which we want to discuss is the advection of vorticity. Let me write that. Advection of vorticity, and a typical example is vortex interaction. So let's do the same. Let's now assume that we have we take our vorticity equation, but now what we do is we assume that the flow is inviscid. So assume an inviscid flow. So we neglect the effect of viscosity, and therefore we're just left with this equation. The material derivative of omega dt is equal to 0. So if I'm assuming the flow to be inviscid and I have just one single irrotational vortex, let's start with the same irrotational vortex as before. Let's say that it's located at, let me now put my origin here. This is x, this is y. Let's say the center of my irrotational vortex is at the point x naught, y. So this here is x naught, and this here is y. So I have a single vortex. From our discussion, from our earlier discussion, if we have a single vortex, well, nothing, and we neglect the effect of viscosity, nothing happens. And the irrotational vortex is just going to stay here. It's not going to move, and the flow is just going to remain the same flow around an irrotational vortex. No radial velocity, and a circumferential velocity, or velocity in the circumferential direction, which decays in 1 over r. So just having one vortex is boring because nothing happens. So let's put another one. Okay, and what I'm going to do is I'm going to put a mirror vortex with the opposite sign here, just to see what happens. So let's say that now I also have a vortex at location minus x naught y. So I have another vortex here, and the velocity and the circulation of this vortex is of minus gamma. Okay, now I see that it's been 40 minutes, so I'm going to stop here, and you can ask your questions to Koen.